there are three properties that a collection of vectors might have. They might span some subset, they might be linearly independent, they might be linearly dependent. And it kind of pays to know how those properties change as you either go forward from the domain to the codomain using a linear map, or backwards from the codomain to the domain. So let's just record how all of these properties interact going either forwards or backwards across a linear map. So for spanning sets forward, if you have a collection that spans a collection of vectors that spans V, then the image of each one of those span the image. And this is because if we have a vector in the image of F, then that means that there is some vector in V where f of v is w, because that's what it means for w to be in the image, right? Something has to go to it. But we have a basis for v. Well, we have a spanning set for v, right? We don't necessarily know it's a basis, but we have a spanning set for v, so we know we can write v in terms of that spanning set. So write v equals a1 v1 plus dot 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 down to a n v n. Then, right, we know that w is f of v, but v is a1 v1 plus dot 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 down to a n v n. Now we can use the preservation of structure, so this is a1 f of v1 plus dot 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 plus a n f of vn. Okay, and look, see, we've written this anonymous arbitrary element of the image as a linear combination of the images of v1 through vn, and that means that f of v1 through f of vn span the image, which is what we wanted to show. So that one's proved. All right, so how about if you have a spanning set on the image side, does that mean you started with a spanning set on the domain side? And the answer to this one is no. So if we have some vectors whose images span the image of f, it need not be the case that those vectors span the original space V. So I just need to give you an example of this. So let's take as our example R2 to R, and we'll define this linear map by f of AB equals, let's say, A. All right, now, so now I need to tell you what is n, right? We're not assuming that n is the dimension of V here. I need to tell you what are my V's. So I'm only going to have one of them, and it is the vector 1, 0, right? So f of 1, 0 is 1, and this spans the codomain space R. But my lone vector v does not span the domain space capital V, right? So just because you have images that span, that doesn't mean that the vectors you started with span. All right. Next thing to think about is how linear independence interacts with linear maps. So suppose we have vectors in V on the domain side that we know are linearly independent. You might think that maybe they should be linearly independent on the codomain side, but that's actually not true, right? They might be, but in general, if you start with linearly independent vectors and you go forwards along a linear map, you might not end up with linearly independent vectors. In fact, our previous example is also an example of this. So 1, 0 and 0, 1, these are linearly independent. So if we hit both of these with f, do we end up with a linearly independent set? Well, f sends 1, 0 to the real number 1. F sends 0, 1 to the real number 0. And these are not linearly independent. You can't have a linearly independent set with the 0 vector in it. So these are dependent, right? So it is not necessarily the case that a linear map turns linearly independent sets into linearly independent sets. It might, but not always. In fact, well, let me not say that. All right, so that's linear independence forwards. What about linear independence backwards? If you end up with a linearly independent set, did you start with a linearly independent set? This time the answer is yes. What we need to do is check in this setup, right? We have vectors v1 through vn. We don't know at first if they're linearly independent, but we do know that if you hit them each with f, you get a linearly independent set. So let's check if v1 through vn are linearly independent. How to do that? Write a linear dependence relationship. So a1 v1 plus dot 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 up to a n vn equals 0. This is the 0 in v. Now we know about linear dependence we know about linear independence in w in the codomain space. So how do we get to the codomain space? Use f. All right, hit both sides of this with f. Now on the left-hand side, we can use preservation of structure. So this is a1 f of v1 plus dot 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 plus a n f of vn. And what does f do to the 0 vector in v? Well, it has to turn it into the 0 vector of w because it's a linear map. But this is a linear dependence relationship among the f of v1 through f of vn. And those, we assumed that those are linearly independent. So a1 has to be equal to 0, and a2 has to be equal to 0, and so on down to an has to be equal to 0. So we started with a linear dependence relationship among the v's. We showed it has to be the trivial one. So this means that v1 through vn are linearly independent. All right. So that's linear independence, forwards and backwards along a map, right? If you're linearly independent on the domain side, you might not be on the range side, on the codomain side. If you're linearly independent on the codomain side, in particular in the image, then you are linearly independent on the domain side. What about linear dependence? So how about forward? If you have vectors that are linearly dependent, then so are their images. And this is pretty easy to show. So let's write a non-trivial linear dependence relationship like this. And this is non-trivial. So that one of these coefficients, at least one of these coefficients is not 0. We want to know about what's happening on the codomain side, so let's move there by using the function. All right, of course we can use preservation of structure. On the left-hand side, we get a1 f of v1 plus dot 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 plus a n f of vn. And then on the right-hand side, f of the 0 vector in v is the 0 vector in w. And here we have a a non-trivial linear dependence relationship in w. Right? We know it's non-trivial because we said at the beginning one of these coefficients up here was non-zero, so one of these is non-zero. So that means that the images are linearly dependent. All right. How about linear dependence backwards? If you end up with linearly dependent vectors, did you have to start with linearly dependent vectors? And this time the answer is no, in general. Now, it might be for a specific example that the vectors you started with were linearly dependent, but that doesn't always have to be the case. So let me give you an example. In fact, we can use the same example we were using before from R2 to R. So that was this, right, giving us just A. So for this, so so now I need to tell you what are the V's. So for V1, it's going to be 1, 0. For V2, it's going to be 0, 1. F of 1, 0. So 0 times f of 1, 0 plus 1 times f of 0, 1 is 0, right? Because this term is 0 because it's multiplied by 0. This term is 0 because f of 0, 1 is 0. So this whole thing is equal to 0. So these two outputs are linearly dependent. But of course, the two vectors I started with were linearly independent. Right. So this function turned a linearly independent set into a linearly dependent set. You can see that what's happening here is this happened because this function isn't one-to-one. Right? If this function were one-to-one, then that would force the v's to be linearly dependent.